Hi, so today we're going to be proving a theorem in linear algebra. And well, this theorem is a really fundamental one, and it just tells us that if we have an arbitrary n by n matrix, which I will call A, well, the space generated by its columns has the same dimension as the space generated by its rows. So let's get this into a bit more detail. If we get this row and so on, and we generate a space, which we'll call BR, and this is an expression for the rows, it will have some dimension, which we'll call dim VR. Likewise, if we get the columns and so on, we'll get this expression for each column, and well, we will be generating our space BC. In this case, the dimension will be dim VC. Well, what this theorem tells us is that this dimension is actually the same as this other dimension. Well, before we get into proving the theorem, let me just do a quick mention about the notation we're going to be using. And well, this C underline J just means that, well, if J is equal to 1, we get the first column. If J equals to 2, we get the second column, and so on. And there are n of them. If you count them, there are n columns. Likewise, if we get the first row with this expression here, the second row, I here will be 2, and so on, until we get to the last row. In this case, there are m rows. This is actually a column matrix, but with this underline, I'm treating it as a vector. And here, this is a row matrix, and I'm treating it as a vector with this underline here. Really, this is just notation, and I'm not actually going to be using that in the theorem, but in the proving the theorem, I will be using this notation. Right? Vectors, which I will write with an underline, will just be expressed as a parenthesis which has its components inside, or their components inside. So that's what we're gonna be doing. Yeah, I don't think there's too much more to explain about this, so let's just get on with the proof. So let me just write here, proof, and well. Before getting on with the proof, let's just say that we're gonna be starting with the space VR. And this space VR is generated by all the rows. So its generating system would be the first row, the second row, and so on till we get to the last row, which is the nth row. SR just stands for generating system. Of course, this linear combination of all this will be able to give us any vectors here. But we can do better. If we don't know if some of these vectors are linearly dependent or not. If they are linearly dependent, we can actually just get a smaller generating system. And the smallest generating system is what we call a basis. And I will use these other brackets to denote a basis. But really, it's just the same as a generating system, but we are making sure that all the components or the vectors of this basis are linearly independent. So I will be saying that, well, we have already found a basis, which we can always do. We have found a basis, and this basis is made up of BR1, BR2, and so on, until we get to the last vector, which will be BRK. Notice that we have gone from m vectors, there are n vectors, and we have gone down to k vectors. But what is k? Well, k, we don't know exactly what k is, but we do know that it is less or equal to m. If all these vectors are linearly independent, it will be m. But if there are some of these vectors which are linearly dependent, we can take them out and we'll get a value that's less than m. So in general, we get that this basis generates this system. And I will just write it up here so it doesn't bother us too much. Just saying that, well, BR, just gonna write like this, is generated by this basis, which is just BR1, BR2, and BRK. Now, what are these vectors VR? Well, these vectors really are just some, not arbitrary, but some vectors that we have found, but we don't know exactly the expression. So this just denotes any of these vectors will be the vector with components B alpha 1, B alpha 2, and so on until we get to B alpha n. And well, alpha goes from 1, 2, so on, until we get to k. So what is alpha? Alpha is just telling us that if alpha is 1, well, we are expressing this vector. If alpha is 2, we're going to this vector. And so on until alpha is k, which we will get to this vector. And the components of each of these vectors, I'll just write alpha to distinguish, well, this is the first component of the alpha vector. If alpha is 1, this will be b11, b12, and so on. So alpha just tells us which vector we're working with, and this 1, 2, 3, and so on just tells us the component of that vector. So let me just write this here because this will be really useful for us. So Br alpha is just B alpha 1, B alpha 2, until we get to B alpha k. Sorry, B alpha n. Remember that these vectors have n elements because they are really just like our row vectors. Each of these row vectors had n components, so our space is a space of vectors with n components. So our basis will need to have vectors which also have n components. Okay, so I just wrote all of that here, and let me just write this again, that alpha is 1, 2, so on until we get to k, and that k is less or equal to the number of rows n. So let me just erase this real quick, and we'll see how we can keep on going. So what does it mean that all these vectors are based off Br? Well, it just means that the linear combination of all of them can generate any vector there. And we know that on Vr, all the row vectors belong there, right? Because that's how we have created Vr actually. So this just means that, for example, our first vector, R1, will be some coefficient times our first vector, Br1, plus some other coefficient times our second vector, plus dot dot dot, until we get to our kth vector. And what are these coefficients? Well, to make notation easy, I will call these coefficients d, well, just like before, d1, and here I'm just going to write 1. Well, maybe I just write it in white. Yeah. So what is this first one? Well, this first one just tells us that we are dealing with the first vector, and we are multiplying it by the first vector. So this is the first coefficient of the first vector. Likewise, d to 1 is the second coefficient. Sorry, this should be a 1 here. This is the second coefficient of the first vector, and this is the kth coefficient. The kth coefficient of the first vector. Sometimes it can get messy with all these subindexes, but if you reason what these subindexes are, you will be more likely to not get mistaken. So, first component of first vector, second component of first vector, and kth component or coefficient of this vector. Likewise, for R2, we get that, well, this is just D2, let me just write D2 and D2, and again, first component, second component, kth component, Br1, this is the same vector, okay, we are dealing with the same basis, Br2, dot dot dot, plus our last vector, Brk. Okay, and we can keep on going until we get to our last vector, R. How many were there? Rm, sorry, there were n vectors here. And again, we have our nth component of our vectors, dm. And well, this is the first coefficient, second one, the kth one, and first vector, the second vector, and this last vector. Now, this is true because all these vectors belong to Vr, and these bases, and these are linear combinations of the bases. So far, we are doing things fine. We are all of this is valid. How do we keep on going from here? Well, a really nice way is to consider expanding the vectors in terms of the components. So this R1 vector is just the first component of R, as I have written here, is just A11, and just A1. I was just writing in pink. A11, A12, and A1n. Let me just explain this real quick. So our I, our first component, means the vector we're dealing with. Here it should be I. So our first vector, R sub I, will have components A1, first vector, first component, first vector, second component, and so on. So to not get mistaken, I will write here this. This is just R1, this is R2, and sometimes you have, if you want to write it like this, you will have to spend some time actually writing it. But I will do it just so everything is really clear. So, again, second component of the second vector, nth component of the second vector. So on, so on, so on, we get to our our nth vector, and this is just A1, sorry, not M, but M. You see, sometimes you might get mistaken. M. Let me just get this out of the way. So again, second component of the nth vector, nth component of the nth vector. And well, if we do the same for each of these ones, we just write D11, D11, D11. You know how this goes, just writing these vectors again. What is this first vector, BR1? Well, BR1 is just given here, and it is just B11, B21, so on, what was it? Sorry, B12 and B1n. Again, alpha in this case is 1, so we have B11, B12, and so on. I'm not going to write this second vector because I don't think I will have space, so I'm just going to skip right into the kth vector. In this case, alpha is k, so we have bk1, bk2, until we get to bkn. Okay? Now, what is this vector? Well, sorry, this should not be a 1, but rather, yes, d21. And this should be dn1. Well, what is this vector? This is exactly the same vector. We just have to write it again, because, again, this is the first vector of our basis. So, b11, b12, so on, b1n, plus, d second vector, kth coefficient, bk1, bk2, bkn. It might seem a bit boring at first, but I will write everything down so you can get a really clear idea of what we are doing at each time. So now, b11 again, b12, so on, b1n, and bk1, bk2, and bkn. And sorry, I think that's too clear. Mk. Yes. So let me just erase this for a minute, because we are going to need to have some more space. So this, what I have written here is just the same as we had before. It's just saying that R1 in its component form is the same as some coefficient times our first vector plus, well, all of these and some other coefficients times our k vector. Again, here our second vector, our second row, is just the same as some coefficient as our first vector times some other coefficient times our second vector, and so on, so on, so on. What do we do from here on? Well, let me just say that we will get the jth component of each vector. What do I mean with this? Well, let's just say that I write again here. Let me just write this again. R, we have our vector R1, but we are going to get the jth component. And what is the jth component? Well, the jth component can be just, for example, j equals 1, we're getting this one, j equals 2, we're getting this one, j equals n, we're getting this one. So we're just going to get one of these components. In general, j will be somewhere between here. So let's just say that j is here, okay? So that is, we're getting one component of this. And with this component, for A1, it's just A1j, right? And this is the same as, well, we still have our D11, but here we have to multiply by the jth component of this one. For example, if I got this one, if I got A11, well, A11 is equal to D11 times this first component, plus so on, so on. So the first component multiplied by the coefficient always. So D11 times our jth component here, which will be B1j in this case. Plus, well, if we keep on going, well, let me just write some more terms. D12 times B2j, D1k times BKJ. Okay, so that's what we get. Each component of this vector has this expression. Likewise, if we go to the second vector, and we get the jth component, this is what the notation means. Well, we're going to the second vector, getting our jth component, and well, here we have second vector first component times the first, jth component here, again just jth component of this vector, which is exactly the same as the one we have before because it was the same vector. So really, we just have 1j plus the second vector, second component, b2j plus so on, d2k, bkj. If we keep doing this, we will get to our last vector, which is just rm, and getting the jth component again, just let me just see it, yeah, amj. Yes. And well, again, what's the first coefficient? It's just dm1 times the jth coefficient, which is just the same for all of these equations, b1j plus dm2. Sorry for the handwriting, it's just that this is not really a good chalk. d2j, yes, and so on, so on, so on, till we get to our last one. Let me just write and dmj, bkj. So I know it might seem a bit messy and there's a lot of writing and it might seem boring, but I think that this is the easiest way to see how this proof works. So let me just erase this again. And well, let's just do a quick check that, for example, we get the jth component here. What do we get? We get a2j, and this is equal to our first coefficient times the jth component, which is just b1j. Likewise, d22, sorry, we get b2j and so on. So that's what we get. So I just want you to notice that all of these terms are actually the terms of the columns. Just bear with me. This Cj was actually just A1j, A2j, and so on until we get to AMJ, wasn't it? But this is the same as we have here, here, and here. So in matrix form, if we write this vector like this, as a column matrix, we have that, well, A11 is just the addition of all of these terms, but we can write them as follows. We can just write A11 is just B1j times our first coefficient, D11, plus B2j times our second coefficient. Sorry, this was just supposed to be a B1j. Our second coefficient, which was D12, plus so on until we get to our last coefficient, which is just D1k. And well, this is weird, so really this should be a column here. And that's what we get. So our first A1j is equal to, well, this first component times B1j plus this second component times B2j plus this last component times BKJ. Likewise, we can just keep doing this, noticing that all these terms are equal, so we can factor them out. These terms are equal, so we can factor them out of the matrix, and likewise these terms are equal, so we factor them out. So B21, so on, until we get to our last one, DM1. Likewise, D12, D22, DM2. And finally, we have D1k, D2k, and our last term is just the mk. So notice that each column is actually a linear combination of some coefficient times vectors, times k vectors. So let me just erase this and explain this a bit better. Okay, so if we call, let me just call D1, this first column, D11, and D21, so on, DM1, and let me just call 2, D2 is just D12, D22, and so on until we get to DM2. Likewise, keeping doing this until we get to our last one, dk. Well, this is just d1k, d2k, dmk. So if we call this, we can actually write each column as follows. So we can write cj as, well, some coefficient, which is b1j. Let me just write it here. Some constant b1j times our first vector d1. Likewise, we add the second term, which is just b2j times our second vector, which is just d2, so on, and lastly we have bkj times our last vector dk. So what is this? Well, this holds really for any j, because we have done it for any general j. So j really is 1, 2, and so on until we get to n. So this holds for any column, for the first column, for the second one, and so on, and you can check it if you want. Oh, sorry. What does this mean? Well, this just means that any column can be written as a linear combination of k vectors. 1, 2, 3, up to k. So there are k vectors, and that's all the vectors we need to construct bj. And actually, all these vectors are the same. the same in the sense that they don't change with J. The only thing that changes with J is our coefficients. So really, if BC is the space generated by Cj, then a basis of that space is let me just say that BC, and let me just erase this real fast. So let me just do it just again from the beginning. We have that BC is the space generated by, well, C1 until we get to Cm, right? There were n vectors. But some of them might be linearly dependent, so on, so on. We get that our basis, as we have proven here, this basis is just, well, yes, it's a basis because they're linearly independent vectors. This basis is, well, it's just d1, d2, so on, dk. So what have we proven here? Well, so far we have that the dimension of k, dimension of the rows, which is k. No, sorry, I made a mistake here. This is not really a basis. This is actually another generating system. And it is a generating because we don't know exactly if these vectors are linearly independent. So really, the dimension of BC is less or equal to k. Okay? That's what we have. It is less or equal to k because we don't know exactly if these are linearly independent. We know that they do generate the space of all the columns, BC, but we don't know if they're linearly independent. So the dimension could be k, but it could also be less than k. But k is actually the dimension of this. So far we have that the dimension of BC is less or equal than the dimension of BR. So this is our first step in our proof, and this second step is going to be actually really easy. So I hope you understand this. We have seen that BC is the space generated by all these vectors, okay? And all these vectors can actually be written as this linear combination. So any vector in this space, okay? So let me just write it like this. So for all Cj belonging to this space, what we have is that Cj, well, we have this. We have that each Cj is a linear combination of all of these, meaning that this generates Vc, which are k vectors, so the dimension is less or equal to k. I hope that's clear. I know I explained it many times, but it's just really important to notice that. So the dimension of BC is less or equal to the dimension of BR. So that's our first step. Let me just erase all of this and get on with the second part of our proof. What we will do now is that we will consider the transpose matrix. Namely, we will consider AT, which is just the matrix in which we change the columns and the rows. So this column becomes a row in this new matrix. This will be A11, A21, and so on until we get to AN1. Likewise, this column becomes the second row, so A12, A22, AM2. So on, keeping on going with this, we get to A1n, A2n, and lastly AMn. Okay, what is the actual definition of this matrix? Well, it's just saying that the rows of AT are the columns of A, and that the columns of AT are just the rows of A. That's actually how we have constructed this matrix. This column corresponds to this row, and this row corresponds to this column. But how does this help us? Well, using this theorem, or this part of the theorem, we said that, well, this was for A, right? That for any matrix, any arbitrary matrix, A is just any arbitrary matrix, A, we have this relation. But this is another arbitrary matrix, really. So here, we actually do have, again, following the same procedure as before, the same relation. So if we had it for A, it must also hold for AT, because there's nothing special about this matrix, really. This is another arbitrary matrix. So the dimension of the columns is less or equal than the dimension of the rows, but in this case for AT. Okay? But notice that because we're dealing with a transpose matrix, BC, in this case, is nothing but VR. That is, this is the space generated by the columns of AT. So BC, I don't know how to write it to make it clear, but so let me just write this. The space of columns of AT is the same as the space of rows of AC. Again, the columns on AT, for example, if we get these columns and we generate some space, we get VC for AT. But this is just the same as getting these rows, which would be generating this new space VR for A in this case. So this means that these two spaces, VC and VR, are actually the same space because they generated by the same vectors. So let me just write this clearer. These columns generate the space BC. But these rows also generate the same space. But in this case, we call it VR. So VC is equal to VR. And this VC really is in AT, and this VC we have generated from matrix A. Likewise, the space of rows for AT is the same as the space of columns for A. So using these relations, which actually just come from the fact of how we have constructed a new matrix, we get that this becomes that the dimension of BC, okay, this should be AT and AT, so the dimensions of BC AT are just the dimension of BRA, so the rows on A, and this is less or equal than the dimension of BRAT, but BRAT is just BCA, so this is just BCA, so we get this other relation. If you want, instead of just using directly this result, you can do the exact same procedure we did for A, and you will actually get to this same conclusion. Now, what does this mean? Well, this means that the dimension of VRA is less or equal than the dimension of BCA, but we also said that the dimensions of BC, let me just write this here, an A, and the dimension of BRA satisfy that. So let me just write this here. BCA is less or equal than the dimension of BRA, but the dimensions of BRA are less or equal than the dimensions of BCA. And this can only hold if both dimensions are the same, because if one number is lower than another number, and that same number is lower than the previous number, they have to be the same, equal, so the same number, not lower, but lower or equal. So from this, it follows that the dimension of BCA is exactly the same as the dimension of BRA. So as we see, we have already proven this theorem. Okay, BC is equal to dim BC is equal to dim BR. Well, this, as I said, just means that if we get our columns and generate a space, it will have the same dimension as the space generated by the rows. I know that the notation and everything can be a bit messy for these kinds of theorems and proofs, but once you do some of them, you will get the hang of it. It's actually really important to see what kind of notation you're going to use. As you can see in this case, I might have gotten a bit mixed up, and I should actually have maybe used some other notation, but I spent some time thinking about the notation, and I thought that this should be clearer. But maybe I had to do some other fixes in the notation for everything to be a bit more understandable and easy to follow. So, well, that's the theorem problem. If you have any questions or any more doubts, I will include a PDF in the description where I follow the same procedure to prove the theorem. Maybe that way you will see it clearer if you have it written down and you can consult it. So, well, that's it for today. I hope you liked the video, and see you in the next video.